So this lesson's on the total differential, but before we look at the case of a function of two variables, let's look at the case of a function of one. So I'm starting with the point xy. I'm moving a little bit over in the x direction, a little bit up in the y direction. So this new point is x plus delta x, comma y plus delta y. And I want to learn something about this location. If I change x a little bit, how far do I expect y to change? That's our basic question. And the way I answer that is I construct a tangent line at the point xy. So let's do that. So there's our tangent line, and the slope of that tangent line is f prime of x. But we have another notation that we use. Do you recall? Another notation we use for the derivative. So what I'm going to do here is, as I'm going to construct the following. So remember, this is the point x plus delta x, y plus delta y. So this distance from here to here is delta x, and from here to here is delta y. So the slope of f prime, the slope f prime of x is not the same as delta y over delta x, but it's pretty close, right? We're going to use a differential to approximate that change in y. What am I going to do instead? The slope is f prime of x. Slope is change in y over change in x. It's this distance divided by this distance. And we know that that slope has got to be dy dx. That's the other notation that we use. So dy is here. We see that? And then this is also dx. So when we let dx be the same as delta x, dy should be pretty close to delta y. But what's our idea here in terms of the differential? Well, we connect these two ideas and we say f prime of x is dy dx. So f prime of x times dx equals dy. But this just kind of feels like playing with variables. But that is our differential. But what do we use the differential for? Occasionally to approximate small changes. And the approximation we're going to use is that the change in y should be approximately equal to f prime of x times the change in x. That approximation will be good when the change in x is relatively small compared to the other elements in this formula. Now, how do we go from that situation with a function of one variable to a situation with a function of two variables? It's going to get a little bit trickier. But our idea is, how far do we expect to jump on a straight line, or in our case, on a plane? So let's take a look at a 3D representation here. So I have a function z of xy, and we're calling this function is z of xy. That is the surface that's in the light blue. My point here is xy. I'm moving a little bit in the x direction, which on this graph is left and right. Moving a little bit in the y direction, which is here. We see that? So this point moves in the x direction and lands here. Then it moves in the y direction and lands there on the tangent plane. So the tangent plane is tan, interestingly enough. The surface is light blue. And we want to determine how far does it move. It starts here. This is my original z value. This is my new z value on the tangent plane. How do I figure that out? How do I find out how much it's grown? How much has the z changed from this point to this point, looking for change in z? Now remember, what did we say before? We said the change in y was this slope times the change in that direction. The slope times the change in that direction. Well, a partial derivative is also a slope. So as we jump back to that, what can we see? The partial derivative of z with respect to x, again, the rate of change of height with respect to a change in x, times the change in x will give me an approximation for how far it's gone up when we move in that direction. And notice this little distance is also moved over there. because this is where we're going to need to see how far it's actually grown altogether. Moving in the y direction, moving in this direction, rate of change of z with respect to y times change in y will give us a change in z, yes, on the tangent plane. And there's my change in z here for that portion. So what's the entire change? It changes a little bit in the x direction, and it changes a little bit in the y direction. So partial derivative with respect to x times change in x, plus partial derivative with respect to y times change in y. And as we can see here, that is our approximation for the change in z. So I would like to clean up this notation a little bit to make it more beneficial for me. So instead, I'm going to say z equals f of xy. So rewriting this, change in z is approximately f sub x partial of f with respect to x times the change in x plus the partial of f with respect to y times the change in y, which then leads me to my differential. What is my total differential going to be? As we shrink delta x and delta y to 0, we get the following. We get dz is f sub x dx plus f sub y dy. That's the differential, although this is the one that we're going to use to approximate things. If you're approximating a change, that's the one that we're going to use. So there's our formula that we motivated with the geometry. Now we want to use that differential to approximate the change in z, so dz or delta z, as xy moves from 1, 1 to 1.01, comma 0.97. So certainly my original x is 1. My original y is 1. My original z is root 4 minus 1 squared minus 1 squared. So 4 minus 2 is what? Root 2. So we have that as our original z. Now how about our change in x? What's our change in x? We're starting at 1. We're going to 1.01, so that's up 0.01. But our original y, or our change in y, original y starts at 1, goes to 0.97, so that's down 0.03. So we have this information. Now I need to take some partial derivatives. We notice we have partial of f with respect to x, partial of f with respect to y, or if you prefer, of course, remember the other notation. Partial of f with respect to x can be thought of as that funny looking dz dx. Partial of f with respect to y, that funny looking dz dy, if you prefer that notation. So what are those partial derivatives? So here's f of xy, 4 minus x squared minus y squared to the 1/2 power. Using the chain rule, 1/2, 4 minus x squared minus y squared to the negative 1/2 times the derivative of the inside with respect to x, which is negative 2x, half of negative 2x, negative x over the square root of 4 minus x squared minus y squared. And similarly, f sub y, 1/2, 4 minus x squared minus y squared to the negative 1/2 times negative 2y, and we get negative y over root 4 minus x squared minus y squared. So here's the information that we have. I know delta x and delta y, so I will use those to approximate dx and dy. I have the formulas for f sub x and f sub y, but I've got to evaluate it at my point of interest being 1, 1. That's what has to happen next. So doing our computation, plugging in 1, 1, we get negative 1 over root 2 for f sub x at 1, 1. And similarly, f sub y is negative 1 over root 2. So what was our rule? What was our total differential? dz was f sub x dx plus f sub y dy. So the change in z then should be approximately f sub x at that value times change in x plus f sub y times change in y. And let's recall what we said a little earlier. Change in x was 0.01 and change in y was negative 0.03. So let's go ahead and approximate our change in z. What do we get? Plugging in those values, negative 1 over root 2 times 0.01 minus 1 over root 2 times negative 0.03. And we get z, change in z is about 0.0141. So we need to think about what this means. So if you recall, we started at the point where x is 1 and y is 1, and then my original z becomes the square root of 2. Well, we've just said that we believe that the change in z is approximately 0.0141, which means what is my best guess for what that should be? Our question was essentially f of 1.010.97. My original z is root 2. My guess for the change in z is 0.0141. So what do I get when I add those together? So using the differential, this is my predicted value. Now, what is the actual one going to be? How good of a prediction is this? The actual value, f of 1.010.97, should be 4 minus 1.01 squared minus 0.97 squared. And what is that approximately? We hope it is somewhere in the neighborhood of what we came up with previously. So my predicted value for that is 1.4279. So again, my dz, what we actually had, right, that was my predicted value. So dz, we said let's use as our predicted value for change in z. dz gave us 0.0141. Change in z really is 1.4279. That was the actual value minus the square root of 2, which is how much? 0.0137. So dz, as predicted by the tangent plane, is pretty close to what we get by just evaluating the two endpoints and subtracting. So as long as change in x and change in y are relatively small compared to the other elements of the problem, then your predicted value for change in z and dz should be about the same.